Hi, and welcome to the continuation on this saga of this lab's power supply circuit. Let's get going. Now, I've filmed parts 2, 3, and this is now part 4 back to back, so I'm kind of lost as to where I am with it at the moment. Where we last left off, I've now got two separate transformer windings pairing the circuit, which is... it's not great. It's still not technically single supply. There are better methods of generating that negative 5 volt reference, which in this video I'm actually going to try one such method. Now, as it is, the circuit is working on roughly 18 volt DC, which is not meeting our prerequisite of 0 to 30 volt. However, I'm pretty sure it can be run on 24 volt. It was running on 24 volt before and it didn't destroy the IC. But with the charge pump circuit in there, because of the way it's configured, it is going to be rectifying, half-wave rectifying, the positive going cycles of the transformer secondary, and it's pumping it into the negative rail. That voltage has got to go somewhere, and it ended up charging up the main filter cap to over 10 volts extra on the BCC line. So I had up to 30 volt there, 35 last time I measured it. And when I measured across pins 7 and 4 of the IC, I had 50 volt DC. I didn't film any of it, unfortunately, but there was 50 volt DC across that IC. It's only rated for a maximum of 44, and that's like 6 volts over its maximum. And I'm surprised it survived. It's the same IC that I'm using in this current circuit configuration now. It's still working. So the charge pump circuit is out. It's obviously not going to work. We discovered that in part 2, I believe it was. And then in part 3, I did a bipolo sort of arrangement for the transformer winding. That again is not single supply, and it's just bad. So that's where we're up to right now. I'm going to be modifying the circuit to use a different form of generating a negative 5 volt reference, and we can actually just use our normal positive rail and our normal common, so we only need a single supply in the end, which means then I can use my transformer at 24 volt. However, with this method I'm going to have to be careful of the voltage that I'm supplying the negative inverter, for want of a better term or word or whatever you want to call the circuit. It does literally invert the supply rail. There is a chip for it. It's an LTC chip. Can't remember the numbers off the top of my head, but yeah, I'd have to order them, and I don't want to do that. So the new method I'm going to try is using a 555 timer, which will be used as a pulse width modulator. And you can also generate this same PWM signal from a microcontroller if you wish, and then it just goes through a simple diode capacitor network to give us the negative voltage required. I will show you a schematic in just a moment. And here's the circuit I intend to try out here. It uses a 555 timer as an ostable vibrator, so it's actually configured as a square wave oscillator. What the actual frequency of that square wave is, I don't know. We could probably work it out between the resistor value and capacitance here, but I can just easily measure it. We have a 680 ohm and shunt xenodiode here to reduce the voltage going into the 555 timer, because don't forget we're going to be coming off the main filter cap, which can be up to 35 volt. These ICs are only rated at 16, so we'd have to have some form of clamping here. And the output current of these 555 timers is up to 200 mA, so I only need to drive a current requirement of 60 odd mA. I calculated it yesterday. We got two 1N4148 diodes as rectifiers. They again can only handle 200 mA running through them, but that's perfectly fine for what we need. Now, when the output goes high, so we'll say it goes to 5 volt, it's going to start charging the plate of this capacitor, and then when it starts to go to the low, it'll discharge the capacitor, and any positive voltage will then be rectified by this diode and shunted to ground. When the voltage starts to rise again, it's charging the capacitor now in the opposite direction. Negative should flow out, which is then rectified by this diode, and then we get a negative volt out here. I also believe on the original schematic that this capacitor is backwards, because this should be the negative voltage reference here compared to COM. So for testing purposes, I will probably not include that capacitor, although it may be needed to have a stable output voltage. I do not know with this arrangement here how much voltage is going to come out. If, say, this was running at 12 volts, it may only be 6, may only be 5, I don't know, I'd have to test it. So I don't know what to make this clamping diode yet. I've got a 12 volt one and I've got a 5.1 volt one. So it'd be up to testing. These two capacitors should be ceramic. I've got two ceramic capacitors of those values, 100 nanofarad and 22 nanofarad respectively. So it's basically just ignoring the shunt part here. It's just two resistors, two diodes and four capacitors. It's dead simple. There is actually a video from the site where I took the schematic from on YouTube, which I will link in the bottom of the description of this video here, just because they actually built it and tested it, and it is uploaded by an Indian YouTuber. Yeah, but it's not like he's uploading a transistor passing DC out to a speaker coil as an amplifier. So yeah, there is that. So that's my intention. Let's get to building this circuit up and testing it. And before I pull this configuration apart, I didn't get around to testing in the last video whether there was noise being presented by having it wired this way to the output. So I'm going to hook it up to my little 100 milliwatt amplifier. If there is any noise or hum or ripple on the output, I should hear it on the speaker. Nearly pulled it apart before I tested that. So I'll hook up positive over here, negative over here. I don't hear any noise except the hiss. Voltage didn't drop that much either. Seems alright. Okay, so it does work like that. But anyway, back to what I was doing. Alright, so I've built up the 555 timer circuit now, oscillator. Got a 5.1 Zener diode as a clamp dropping regulator there. So we're getting about 5.1 volts at pins 8 and 4 respectively. Now I'm just going to plug it in. I haven't got the rectification circuit built yet. I just want to verify that the thing is actually oscillating. So I've got my multimeter there on the frequency scale because I don't know what frequency it's oscillating at. So my oscilloscope only goes to 200 kilohertz resolution. So let's find out. Plug it in. 3.3 kilohertz. We should be able to see that on a scope. And indeed we can see it on an oscilloscope. It's 4.55 volt peak to peak roughly, so when you do the math on that, that's about 2 odd volt and some change peak. 50% duty cycle, so okay, yeah, and definitely 3.378 kilohertz. It's not a perfect square wave, but it is configured as a square wave, which is exactly the output I expect to see. And the frequency seems to be remaining stable, as does the voltage. So now I'll build up the rectification circuit side of things, and we'll see what sort of output voltages we get. Well, I've got the diodes and capacitors in now. That capacitor on the output is indeed definitely drawn on backwards on the schematic. Positive goes to the negative rail, and we have a negative 3.1 odd volt out. It does keep jumping around, but it will stabilize. The Zener diode needs to be higher. I'm probably thinking more like a 9 volt Zener. Then we should have the full 5 volt rail out. However, that's good for testing, so what I'll do is I'll hook that now up to the rest of the circuit and test to see that it actually works. I did it again. I blew up another NE5534. Well, it started to spark because I plugged it in one hole wrong. So I don't trust this IC anymore, so this is another dead one. So, but I've changed the IC to a fresh one because I was taking the ICs out of the breadboard, so I wasn't putting voltage up in the wrong places I didn't want it to be. But it's working now, and I didn't bugger the LED this time, so current limiting is still working. Got 7.5 volt on the output, and I've noticed now there's not much of a drop in voltage when you connect a load. So that's good. I've actually got a -6 volt reference to the circuit, because if I measure at my negative generator here, well, it's dropped down to more like -4.79, but that's okay. It's got a 12 volt Zener there instead, so that's perfectly fine. I just got to check that my resistor is not getting overly hot. That's dropping the current. No, it seems fine. Okay, I'll drop it down to 0. And it's not 0 because I was playing with the pot when I didn't have the positive connected up to the oscillator. So I'm going to have to play with the pot again. See if I can get that back down to 0. Which I can. Not too far. I reckon that needs to be a 2K pop, not a 1K pop, because this is getting kind of annoying. Okay, I'm going to say roughly about there will do. It's not perfectly 0. Wind that up. Full voltage is 18. We are not injecting any more voltage, phantom voltage, onto the positive line. So, I'll drop it to 12. Look at that. Regulates beautifully. That's for current limiting. It does limit, but not by much. Okay. Well. Oops. There we are then. I should run it on the full 24 volt voltage now, shouldn't I? See if anything blows up or whether it maintains its regulation and works properly. Now the NE5534 requires a maximum supply voltage of ±22. However, that does not mean one side has to be +22 and the other side can be any voltage you want. So if I had 5 odd volt on the negative side, I can actually have a higher potential on the positive side. So 22 volt minus, say, 5 volt from 22, that gives us 17. So then we can add 17 volts to the 22 on the other side. That's roughly 39 volts. So that's well within the margin of safety. So 39 plus and -5. Alright, transformer's reconfigured. I'm just going to make sure nothing is shorting on this circuitry, which it doesn't appear to be. Alright, the output voltage is probably going to jump up because it's a different potential now. Here we go. Oh no, it remained around about 12. Sweet. So, nothing went off with a bang. So I'll just verify what's coming out of my oscillator circuitry. It's closer to -8 volt now. I might drop that Zener diode back down. And the supply voltage is 32 that side, but between that and negative, or our reference, it's 41 volt. That should be fine. Let's hook this back up to the output. I'll wind the voltage control up. Right, so the maximum we can get out of this is 24 volt. Okay, that's still reasonable. It wasn't the 30 I was going for, but yeah, it is what it is. I'll drop that to 11 volt if I can get hold of the spindle. try loading it. Drops down in voltage. And for some reason, okay, I might have to change that Zener diode. Zener diode change, let's see what the voltage is. Minus 1.9. Okay. What's our output voltage doing now? So it's 6 odd volt. Yeah, do you ever get the feeling you're doing something wrong? That should not be happening. That resistor's getting red hot. That IC is fine. Right, on that note, I've come to the conclusion that this is not going to behave itself at 24 volt AC. So I'm going to leave it at 15 volt. It may be okay at 18, but it's still a usable supply. I've also come to the conclusion that I'm going to need to probably have a load on the output all the time, just to keep that from wandering around from zero. So I might put an LM334 on the output and set it to a current of roughly, I don't know, 1 mA, 500 microamps, something like that, just to keep this negative voltage from happening. All in all, it works. I can get almost 18 volt out of it, so that's good. So yeah, that's where it's at now. So I'm going to have to change my design parameters to meet the outcome. However, that oscillator circuit at this voltage is working fine with a 12 volt Zener, and I'm getting a good steady negative 4.7 out. And that capacitor's positive goes there, by the way. So if I move my meter probe to the negative reference, well, it's now jumped up to negative 4.8, but it's close. Now, I don't know if that's respective to load, however. It does start dropping down when it's loaded. So that's something to keep in mind. Although it's not doing too bad. And as for the output voltage, when you put a load on it, it doesn't drop down much at all. It actually increases by a couple of millivolt. That's okay. So what I want to know is, as a load now, how that little 100 milliwatt amplifier works powered from it. Seems okay to me, apart from a ticking sound coming from somewhere. I think it's the TL072 IC, to be honest. Voltage does not change at all when I do that. It's remaining perfectly stable at 8.7 volt. As for any noise and hum, all I can hear is the hiss from the speaker. So, as a lab supply, that's working wonderfully. I'm happy, but I might invest in an LM334 on the output there. I just verified that NE5534 is indeed rooted, because as soon as I plugged it back in the board, the LED lit up, so it went current limit, so I reckon the output's shorted. So they must be doing some excavation work next door. There's a lot of noise going on, machinery there. Anyway, I get sidetracked. Now, I'm going to go to work this afternoon, and whilst I'm there, I'll pop into JCar and I'll pick up an LM334. I didn't really want to spend any more money today, but it is what it is. And I'll make sure that the output is loaded, and that's going to be the final test, I think, for this video. I would like to build up my little 12 volt regulator that I was going to use to supply the relay which I was going to use to connect and disconnect the load, and also the panel meter, plus the power LED, so it goes off with the supply. But yeah, I think that can be done. in another video because the content of this one is going on way too long. It is a shame, however, I can't use 24 volt off that transformer. However, with one of these, I can easily build two modules and use either side to give me two separate windings to power two different circuits. Therefore, I can get a dual supply out of it. So 0 to 18 on one side and 0 to 18 on the other. And yeah, I can test op amp circuits with it if I want. I mean, that's all I really need a supply for, is variable, so I can power 9 volt circuitry, 12 volt circuitry, bipolar circuitry, not so much for testing power amps. The only problem with this transformer is I have limited the current now down to 3 amps, but that was one of my prerequisites, at least up to 3 amps. 2 amps is good, 3 amps would be better, but in its current configuration it should suit my purposes just fine. Excellent. Just finished work and having a beer. Cheers. Now, without making this video too long and boring, as I always end up doing inevitably anyway, the dropper resistor or current limiting resistor for that Zener diode, which is a 12 volt diode, is too high, probably in the order of a factor of 3, because we've got 8.75 across that diode and ground. So as the voltage, input voltage fluctuates, the voltage there is also going to fluctuate. I'm going to have to recalculate that resistor properly, which means our output voltage will increase, and I don't know how that's going to affect the circuit, but we're about to find out. So if I go from the Zener diode to my negative reference line, we've got 4.72. Okay, it's okay. I could leave it well alone, but yeah, I'm going to calculate it properly. So to work out resistor value, it's the voltage in, or the supply voltage, minus the voltage of the Zener, which is 12 volt, divided by the current that's running through the Zener. I don't know exactly what current is running through the Zener at the moment, so the easiest way to determine that is I'll just measure the voltage drop across that 680 ohm resistor once I untangle all my wires, and that'll give us an indication of what the current is. So carefully connect these up without disturbing too much. Beauty. Forget the fact that it's minus, we've got a voltage drop of 10.6 volt. So 10.6 volt drop divided by our resistance, which is 680, gives us a current of about only 15 milliamps, which is bugger all. So using that equation, I'll now plug in those numbers. Okay, so we'll remember 15 milliamps, and we've got a supply voltage of roughly 20 minus the voltage of the Zener, which equals 8, divided by 0.015. We need a resistor value more in the realms of 533 ohm. Don't exactly have a 533 ohm, although 680 would have been closer, but apparently not. Okay, we need to work out also what the power factor of the resistor needs to be, or how much current is going to be going through the resistor, so we know what wattage resistor we need. So we know it's 12 volts multiplied by 0.015. Okay, it's only like 180 milliwatts, so that should be fine. So, okay, so I pulled that 680 out and I put a 470 in. So now, measuring across the diode, I'll just plug it in. Now we're closer to 10 volt now. This is what breadboarding is, messing around with values of components. And we've got more like minus 6 volt there now, which is probably going to be a bit too high for the circuit to operate correctly, so I'll just verify. It seems to still be functioning okay. The DC offset's now changed. Okay, so I'll try a 330 ohm now and see if that makes a bigger difference. So it's still a bit low. Okay, 330 ohm is in. I have to plug it in now and see what we get. That's a bit more like it. So now we've got 11.62 volt. I'm going to call it at that. Just going to make sure that that resistor's not getting too hot, because no, it is warming up, but it's not getting overly hot. Okay, so I'll measure my negative voltage rail now. We've got -7.96 there. This now does give me the opportunity to use my negative voltage regulator to actually get exactly a steady -5 volt, which is exactly what I'm going to do, to be honest. Okay, I did something that you may or may not agree with. I've now changed the 1/2 watt resistor from a 330 ohm to a 220 ohm 1 watt carbon resistor. And it is getting warm but not overly hot. We've got 12.35 volt coming across that Zener diode. And now, if I move to the output of the regulator I just installed, bam, -4.91 volt. Yay! Just what I like to see. So as for what the output is doing, bugger all. So I now need to adjust my 0 set pot again to get close to 0, and then we'll talk about the LM334, which I have just purchased a couple of. Actually, we'll see if it remains stable. Ya bastard. So I might go in the millivolt range and see if I can trim that out. I'm assuming I'm going the wrong way. If I can get it dead on 0, I'll be a happy man. Nope, no such luck. It's close. Now, as soon as I move the screwdriver, it's no longer close. Yeah, 2 millivolt. As we can see, the output is still jumping around. Actually, what is the voltage before that regulator? Which is there. Ah, 9 volt. Cool. So we're regulating it down to 5. But the output voltage is still jumping around until I load it with my test light. It remains at 0. Okay, so let's talk about the LM334, shall we? So what is the LM334? Well, it's a constant current source, and what it's designed to do is provide either a 1 milliamp to 10 milliamp, as set by this resistor, constant current source to whatever load that you're connecting it to. Now, there's two ways it can be connected in this configuration between positive and negative something like the output of a regulator, or it can be in series with something like a long tail pair input stage on an amplifier, for instance. And you can set the current, constant current that's going through that input stage to 1 mA if you want to. It comes in 2 packages, as far as I know. The T092 standard transistor style, and a SOT package, or SOT package, for surface mount. It has 3 pins, 1, 2 and 3. Pin 1 is the negative voltage reference, pin 2 is our R set point, and pin 3 is the positive voltage reference. The maximum voltage you can present across this device is 30 volt DC. If you want 40 volt DC, you'd have to use an LM134 or 234. I don't know why it's 10 volts difference between those two and this one, but yeah, it is what it is. Anyway, to work out the value of R set, it is 67.7 millivolts, which is its internal reference voltage, divided by the desired I set current. So if you wanted, say, 1 mA here, well, 67.7 divided by 1
is 67.7. So to have 1 mA or abouts, I'd have to use a 68 ohm resistor there. And that's exactly what I'm going to do. And in the data sheet it says the minimum resistance cannot go under 6.8 ohms, so keep that in mind. Anyway, let's fit that to the circuit and see if that keeps the output voltage stable when there's no load. No, it doesn't. Even with a 10 ohm resistor as R set, which is closer to 9 mA, it's still jumping around all over the place. So I don't know how I'm going to fix that, but it just does not want to behave itself and remain stable. So the LM334 is not going to help in this situation. However, all we have to do is fart and it moves. But anyway, that aside, it is working, and it's working well for what it is. So I'm going to pretty much leave it as it is now. And what's the next step for this? Well, making out a printed circuit board, I guess. I do have to do a small little transistor shunt regulator that comes off the AC side of the transformer on the secondary to give us a 12 volt rail, but I'll do that off camera. I'm not going to bore you any longer with design aspects to this. It is functioning well enough for what it is, so I'm just going to leave well alone. I'm not even going to worry about including the LM334. It was worth a shot. It proved not to help. It's just, I think, mostly to do with the capacitance of this breadboard here is also affecting stuff as well. If it was on a proper printed circuit board, it probably wouldn't be experiencing anywhere near the fluctuation we are. Fuck. So anyway, to end this video off, I'm just going to wind this up to about 10 volt, load it with my test light, and it's still functioning beautifully. It doesn't change with load too much. That's great. That's how it should work. Just for completeness, let's look at our voltage regulated side for the minus 5 volt reference. When I load the circuit, doesn't even change. Not at 330 mA anyway. So at least the reference voltage is remaining relatively steady and constant. So that is the solution I'm going with. Is the 555 timer and this diode and capacitor rectifier circuit here, inverter circuit, and obviously the 5 volt regulator. The 1000 microfarad capacitor is back in circuit, by the way. So anyway, I'm going to leave this video here. I hope you enjoyed it. The next video should be about a printed circuit board, hopefully. I'm going to spend the rest of Easter laying that out and painstakingly going through the design, and I will check back on this in the future. Anyhow, this is going to be probably uploaded after Easter, so I'm going to say Happy Easter anyway. But this is the Astro 30, and if you enjoyed this video, please remember to rate, comment, subscribe below, and you can always follow me on Facebook or become a Patreon supporter for as little as $1 a month. I'd like some more supporters, please. Anyway, this is the Astro 30 saying, see ya. Have a great day. Well, it's working. I'm happy. Now I've got 2 episodes of this to edit. That's nearly 3-4 hours worth of footage. Oh my lord, what I do for you guys. It's all good.